put all our ideas from the previous video on kind of more rigorous definitional footing. So before we get to our main definitions, here's just some background. So let's assume f is defined on an open interval I, and that all derivatives exist on I. We say two functions f and g agree to order n at x is equal to a if their derivatives up to order n at x is equal to a are all equal. So f of a is equal to g of a, f prime of a is equal to g prime of a, f double prime of a is equal to g double prime of a, all the way out to the nth derivative of f at a is equal to the nth derivative of g at a. A different way to say agree to order n is f approximates, not f approximate f, but f approximates g, or g approximates f, to order n at x is equal to a. And so what's going on here, in the previous video, we essentially argued that h of x is, and f of x are agreeing to order 2 at x is equal to 0. So given this setup, here comes our definition of the Taylor polynomial. So t sub n is going to be the nth Taylor polynomial of f centered at x equal to a, and we're going to define that. We're going to define that as t sub n of x is f of a plus f prime of a divided by 1 factorial times x minus a plus f double prime of a divided by 2 factorial times x minus a squared plus f triple prime of a divided by 3 factorial times x minus a cubed, all the way out to the nth derivative of f evaluated at a divided by n factorial times x minus a to the nth power. So in general, let's just write out the first couple of Taylor polynomials here. That marker has seen better days. T sub 0 is just going to be f of a. T sub 1 is going to be f of a plus f prime of a times x minus a. T sub 2 is going to be f of a. I guess I really should be writing of x in here. Not too big of a deal. Plus f prime of a times x minus a. Plus f double prime of a divided by 2 times x minus a squared. And t3 of x, f of a plus f prime of a times x minus a plus f double prime of a divided by 2 times x minus a squared plus f triple prime of a divided by 3 factorial, that's 6, times x minus a cubed. Okay, so this is going to be, these are the first several Taylor polynomials. So you give me a function, and you tell me a particular value of a, and you can just plop things into this formula after taking derivatives to get your Taylor polynomials. I'll just point out, this is our linear approximation. So we are circling back to stuff again from Calculus 1. Okay, why are we defining our Taylor polynomials in this way? Well, this theorem here tells us that this is the choice we want to make. The polynomial t sub n centered at x is equal to a, it agrees with f to order n at x is equal to a. We're using that work from the first slide of this section, of this video, to agrees with f to order n at x is equal to a, and it's the only polynomial of degree less than or equal to n with this property here. So we're not going to fully prove this. However, it is worth just kind of noting that if we write out t sub 2 of x, it's not too hard to see that, yes, it does have this property. So t2 of x, once again, is f of a plus f prime of a times x minus a plus 1/2 f double prime of a times x minus a squared. The derivative here is going to be f prime of a. So this is a constant, so its derivative is 0. We're looking for x's here. The derivative of this is just f prime of a. And chain rule here says this is f double prime of a times x minus a. And the second derivative just ends up being f double prime of a. So we see here T2 of a is going to be f of a plus something times 0 plus something times a minus a is 0. So T2 of a is f of a. And T2 prime of a is f prime of a plus f double prime of a times a minus a is 0 is f prime of a. So T2 and T double prime of a is equal to f double prime of a. So T2 of a is f of a, T2 prime of a is f prime of a, T2 double prime of a is f double prime of a. Everything is checking out here. Basically, this is showing that what we did in this sheet, what we did in this sheet back in the previous video, is just doing this more generally. Okay, so we are close to being ready for our first actual example here. Before we do our first actual example, just a little bit of notation here. Tn of x, we can write this in succinct summation notation. The sum from j from 0 to n of the jth derivative of f evaluated at a divided by j factorial times x minus a to the jth power. The 0th, I'll just kind of point out here, f0 of a, by definition, is just f of a. Also, I'll just point out that we've been discussing Taylor polynomials. Another term that is useful to know here is that if a is equal to 0, we can call these Maclaurin polynomials. So that's going to be when we are plugging in a here. So x minus a plugging in 0 here for a. So x minus a just becomes x. Okay, so our first example of this section, find T3 and T4 for f of x is equal to e to the x. Center that a is equal to 0. So that tells us that these are Maclaurin polynomials. Not just Taylor polynomials, but Maclaurin polynomials. If you just want to call these Taylor polynomials, that's fine. It's just helpful to know that when we say Maclaurin, we mean a is equal to 0. We need some derivatives here, right, to calculate this. But f prime of x is e to the x. F of x is e to the x. F prime of x is e to the x. In fact, all our derivatives are e to the x. Okay, so we need to plop in a into all of our derivatives. A is 0, so f of 0 is equal to f prime of 0 is equal to f double prime of 0 is equal to f triple prime of 0 is equal to f quadruple prime of 0. All of those, e to the 0 is 1. So at this point, we can just go ahead and write down our Taylor polynomials, our Maclaurin polynomials. T3 is f of a, that's 1, plus f prime of a divided by 1 factorial, 1 divided by 1, times x minus a. A is 0, so that's just x. F double prime of 0 divided by 2 factorial, that's 1 divided by 2. X minus a, that's x minus 0 squared, that's just x squared. So 1/2 x squared, and then we need one more term to make this a cubic polynomial. That's going to be f triple prime at 0 divided by 3 factorial times x minus 0 cubed. If we do T4 of x, we get 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1 over 24 x to the 4th. And so these are our not linear approximations, but Taylor polynomial approximations to e to the x. And to finish off this video, I'm going to show off here in the textbook this graph here. So you can see that reddish pinkish curve is e to the x. This blue line here is t1 of x. It's the linear approximation. It's not bad close to 0, but it's pretty bad further away. We can see that the orange and the green curves do much better jobs at approximating e to the x. Not perfect, but much better jobs. So higher ordered Taylor polynomials do a better job at approximation. Okay, we'll have a lot more to say in future videos.